In today's video, we're going to look at section 2.1, Systems of Linear Equations with Unique Solutions. In this section, we're going to introduce the idea of Gauss-Jordan elimination and look at the method of how we can solve systems of equations. So far in chapter 1, we looked at if we had two equations, each one was in two variables, and we looked at the intersection points of the lines. So we went ahead and solved it as a system of equations. But now we want to know what happens if we have more or less equations and if we have more or less variables. How is this going to work? Let's say we had 4 equations in 3 unknowns or 3 equations in 4 unknowns. Can we find some kind of solution to the system? And that's where Gauss-Jordan comes in. The way that it works is by systematically simplifying this system using what we call elementary row operations. So we start out with our system of equations in however many variables, and we go ahead and we simplify down this system of equations to get it as simple as we possibly can without changing the solution of the equations. So we just try and simplify them as much as we can without changing their solution. And that's where these elementary row operations come in. And it's our idea of how we simplify them. When you start this process, we have to make sure of one thing in particular, and that is that all of your equations are in general form. Okay? Remember, that means that all of our variables and their coefficients are on the left-hand side, and any constant is on the right-hand side. So an example of this, do a quick example. An example of this would be, I'm going to have 3 equations here in 3 unknowns. Okay. What you will also notice here is that I have lined up my variables so they look like they are in columns, and that is a very important thing here. I have all my x's under one column, all of my y's under one column, and all of my z's in one column. Okay, so I've lined them up underneath one another. I've done that so that when you go ahead and look at this in a minute to solve it, it's going to actually help us out. So I would highly recommend that before you do anything and before we even discuss how we simplify this in order to solve it, I would highly recommend that you, number 1, write your system in general form. That is absolutely required. But number 2, that you write it in this way where you put all of your variables in separate columns. Okay, the 3 operations that we are going to apply here are these elementary row operations. These are the 3 operations that they're going to manipulate this system without changing the solution to this system of equations. So they keep all of the solutions the same. It's just a way of manipulating these 3 equations so that it is simpler to solve. So what are these 3 elementary row operations? The first one is interchanging 2 equations. All that means is swapping them around. So I can literally just say, okay, my second equation is now my first equation, my first equation is now my second equation. Doesn't change the system at all, but it can make it easier to solve down the line. So that's the first thing. The second thing that we can do is to multiply both sides of an equation by some non-zero number. Okay? Again, it won't change the solution to our system in any way, because you can simplify that equation again by just dividing by that number. It doesn't make any difference to what our solution is. It's actually making it slightly more complicated in the short term, but it can help us in the long term to solve this problem more easily. The third thing, I'll do this on a new page. The third thing that we can do is to add a multiple of one equation to another equation. Again, looks like it's making it more difficult in the short term, but in the long term, it can really help us to solve this system of equations. To show you how this works, I'm going to do this on a simpler system to start with, and then we will do it for a larger system like this 3 by 3 here, where you've got 3 equations in 3 unknowns. But I'm actually going to start out with 2 equations in 2 unknowns. So it's something very similar to what we saw in chapter 1, but I'm now going to use these 3 elementary row operations and show you how they work in order to then use it for a larger system. So these are the 2 equations, and I want to solve them simultaneously, find that intersection point using this Gauss-Jordan elimination method, using these 3 elementary row operations. There is actually an even simpler way of doing this using matrices that we're going to look at the end of the chapter, but for right now I'm going to leave them as equations. Like we said before, the first thing to make sure of is that they are in general form, meaning that all of our variables are on the left and any constants are on the right. Next thing I'm going to do is actually label my equations, equation 1 and equation 2. I always recommend that even if you have to use our first elementary row operation here of interchanging 2 equations, try to make it so that your first equation has a coefficient of x of 1, so that the first term here, whatever that term may be, it's actually a 1 if you look at it, because it's 1 times x is x. But make sure that the coefficient of that first variable in the first equation is 1. Okay, so in this case, our first variable is x, and we make sure that its coefficient in equation 1 is 1. If it is not, interchange 2 equations so that, let's say that the x in equation 2 had a coefficient of 1. Switch the equations around, so make that second equation your first equation. Or you may have to multiply or divide that equation through by some non-zero multiple. Okay, so for example, if we had, instead of this, if we had that this x had a 1/2 in front of it, I would multiply my whole equation through by 2, and that would make sure you do it to both left and right, but then that would give me a coefficient of x of 1. So keep that in mind. That's the next thing that we've got to keep in mind. That's already the case here. We have that coefficient of 1 for our first variable in our first equation. So I can go ahead and start using this Gauss-Jordan elimination method. What you want to do, once you have a coefficient of 1 of that first variable, I want to eliminate the x variable from every equation below the first equation. Okay, let me say that again. I want to eliminate, in this case x, my first variable, from every equation below my first equation. What you're going to do after that, and how this carries on, is that you eliminate the second variable from every equation below the second equation. You would eliminate, if there were more variables, the third variable from every equation below the third equation. Okay, so here my first variable is x, and I want to eliminate x from every equation below my first equation. How do I do that? Well, this is where our third elementary row operation comes into play. I'm going to add a multiple of one equation to another equation. I want to eliminate the x term from my second equation because it's below my first equation. So I want to eliminate x from everything below the first equation. So to eliminate that negative 5x term, I'm going to add 5 times my first equation to my second equation. If I do that, and you'll see why this works. So if I multiply, my second equation is now going to become my original second equation plus 5 times my first equation. So I take what my second equation is here, and I'm going to add 5 times what my first equation is. So I'm going to get negative 5x plus 5 times x. That eliminates the x term. Then I've got 6 times y plus 5 times 2 times y. That's going to give me 16y. And then equals, I'm going to get 1 plus 5 times 3. That's going to give me 16. Okay. So you'll see what that has done. It has eliminated that x term because I would get negative 5x plus 5 times x. So I've eliminated that x term. So first thing we've done is we have eliminated x from everything below my first equation. Now we're going to repeat this process again. So you saw what we did the first time was we took our first variable in our first equation, made sure it had a coefficient of 1. I then eliminated my first variable from every equation below my first equation. I'm now going to do the same thing with my second variable. I'm going to make the coefficient of my second variable in my second equation 1. So I need to make this y have a coefficient of 1 in my second equation. So the second variable has a coefficient of 1 in my second equation. I then, if I had more equations here, I would eliminate my second variable from every equation below my second equation. I only have 2 equations here, so I don't need to do that. But that is how this carries on. So to kind of sum this up before I do this, you make sure that you have a coefficient of 1 for your first variable in your first equation. You then eliminate that first variable from every equation below your first equation. Once you've done that, you look at your second variable in your second equation. So y is my second variable. I then eliminate that second variable from everything below my second equation. Again, here I only have 2 equations, so I don't need to eliminate it from anywhere. But I still need to make sure it has that coefficient of 1 before I do anything else. So I just divide that equation through by 16, and I get y is equal to 1. That is called forward elimination. I now need to do backward elimination. So you'll see I have almost like this upper triangular form to my system. Okay. The goal here is that I actually end up with more of a diagonal form to my system. So what I now want to do is to go backwards. Starting at my last variable, in this case I've only got 2 variables, so y would be my last variable. Starting at my last variable, I want to eliminate that variable from everything above my last equation. So I now want to eliminate y from everything above that second equation. So my second variable ends up being my last variable in this case, but I want to eliminate this term. Make sure you have your system in this upper triangular form and you have done a full forward elimination before you go and do a backward elimination. So to eliminate that 2y, I've got to do a similar thing like I did here. I've got to instead this time adjust my first equation. And I want to make my first equation such that it is my old first equation minus 2 times my second equation. That would eliminate that y term. So you use that variable, my last variable, to eliminate that last variable from every equation above my last equation. What does that give me? That gives me x. I've got no y's now because I'm subtracting 2 times my second equation, is equal to 3 minus 2 times 1 gives me 1, and I'm still left with y is equal to 1. That has fully solved my system. I now have x equals 1 and y equals 1. Okay. Let's do this for a 3 by 3 system, meaning that we have 3 variables and 3 equations. And then I'm going to state all of the steps that we have done so that you have it written down. Okay. So we're going to solve this system using that Gauss-Jordan method. Again, first thing you need to do, make sure that you have every equation written in general form and you line up your x, your y's and your z's. Okay, so that all the variables of like term are underneath one another. Label them equation 1, equation 2, equation 3. Now, go through the same steps as before. I want to make sure my first variable, being x, has a coefficient of 1 in my first equation. If not, I have to use one of my first 2 elementary row operations in order to make that so. But I've already got that here, okay? X has a coefficient of 1 in my first equation. If not, you have to swap 2 equations. If one of these, let's say, had a coefficient of 1, you could swap the 2 equations. Or you could take your first equation and multiply it or divide it by some number in order to make sure that you had a coefficient of 1 for x. Now that we have that, we've got to eliminate x from everything below my first equation. Eliminate your first variable from everything below your first equation. So start out with your first equation. That does not change. My second and third equations are going to change. So my second equation is going to become my old second equation. Now I have to eliminate this x term. So I'm going to subtract 2 times my first equation. Because if I do 2 times this x here, it's going to eliminate the 2x term here. So if I do that, I'm going to get no x term, and then y minus 2 times y is going to be negative 3y. And then 2z minus 2 times z, I actually end up with no z term here, is equal to 10 multiplied by 2 times 8, which is going to give me negative 6. Now what happens with my third equation? My third equation, remember, I've got to get rid of this 3x term. I've got to eliminate it. So I'm going to take 3 times my first equation away from my third equation to eliminate that 3x term. So my new third equation is going to be my old third equation minus 3 times my first equation. Again, I end up with no x term. Then I'm going to get y minus 3 times 2y, which is going to give me negative 5y. And then I'm going to have negative z minus 3 times z, which is going to be negative 4z. is equal to 2 multiplied by 3 times 8, which is negative 22. Okay. So I've eliminated my first variable from everything below my first equation. Now I need to look at my second variable in my second equation. So I need to look at y in my second equation. I want it to have a coefficient of 1 before I do anything else. At the moment, it has a coefficient of negative 3. So what I'm going to do is I'm going to divide my second equation here by negative 3. Remember, you have to do it to both sides. So if I do that, my first equation, is going to remain the same. My second equation is going to become y is equal to 2. We've actually already solved for y, which is great, but we need to carry on and do this for the rest of the equation so we can see what the full solution is. And I'm going to keep my third equation the same for right now. So I now have that my second variable in my second equation has a coefficient of 1. Now I'm going to eliminate my second variable from everything below the second equation. So I've now got to eliminate this negative 5y term here. How do I do that? Well, I use the y above it in order to eliminate that negative 5y. So I'm going to take my third equation, my new third equation is going to become my old third equation plus 5 times my second equation. So my first equation remains the same. My second equation remains the same. And now my new third equation is going to be my old third equation. And then I'm going to add 5 times my second equation. Okay. If I do that, it's going to eliminate that y term. And then I'm going to get negative 4z plus 5 times nothing. So that's going to still end up at negative 4z. And then my constant is going to be negative 22 plus 5 times 2, which gives me negative 12. Okay. Now I need to make sure that my coefficient of my third variable in my third equation has a coefficient of 1. If I have more equations, I would then eliminate my third variable from everything below my third equation. Again, we only have 3 equations here, so we don't have to do that. But I am going to make sure that that z in that third equation has a coefficient of 1. So to do that, I'm going to divide this equation through by negative 4. And that tells me that z is equal to 3. Okay. So I have got it into this upper triangular form. Okay. I want it in diagonal form. I really want this y and z to be gone. Normally you would have a variable here too, but that just so happens to have a coefficient of 0, so it's been eliminated already. But I am now going to get rid of that y and that z in that first equation. That's where the backward elimination comes into play. So I'm going to use my last equation to eliminate my last variable from everything above the last equation. So I'm going to use this last variable, z, in my last equation to eliminate everything above that. So I'm going to eliminate that z using this z. So I'm going to subtract my third equation from my first equation. That's going to give me z minus z, eliminates the z, and that's going to give me a 5 for 8 minus 3. That y remains the same, that z remains the same. So I've eliminated my last variable from every equation above my last equation. And all I did there, just so that we've got it written down, I took my original first equation and I subtracted my third equation from it. Now I still need to get rid of this 2y. How do I do that? Well, I'm then going to use my second to last variable to eliminate it from every equation above my second to last equation. So I'm going to use this y here, this equation, to eliminate that variable from everything above it. So to do that, I'm going to take my old first equation, being this, and subtract 2 times my second equation from it. That's going to leave me with x is equal to 1, y is equal to 2, and z is equal to 3. And like I said, all I did was I took my old first equation and I subtracted 2 times my second equation from it. Okay. And it leaves me with what we call this diagonal form, and it's given me a unique solution where I've got x is equal to 1, y equals 2, and z equals 3. Okay. So how have we done this? I want to make sure that we have this written down. We've got to go through our forward elimination and our backward elimination. So first thing we did when we did this Gauss-Jordan, okay, we made sure that the first variable in the first equation had a coefficient of 1. Okay, then we're going to eliminate that first variable from every equation below the first equation. Okay. Next thing, you're going to make sure that your second variable in the second equation I'll actually put here, second variable in our case was y. Make sure it has a coefficient of 1 in the second equation. Okay, then you're going to eliminate that second variable from every equation below the second equation. Okay. You're going to carry on in this way for your third variable, for your fourth variable, etc. So you carry on in the same fashion until you have this upper triangular form. Once you have done that, you're then going to work backwards. So you're then going to do backward elimination, where you then use your last variable from your last equation to eliminate that variable from everything above the last equation. You then do this with your second to last variable, in our case y, and you're going to eliminate that variable from everything above the second to last equation, and you carry on in that fashion. Okay, so you're just going to carry on variable after variable, working backwards this time. So we worked forwards through x, y, and z as we moved down to get it into upper triangular form. Now you're going to move backwards, so you're going to eliminate z from everything above the third equation. You're going to eliminate y from everything above the second equation. So you work backwards. You work x, y, z, and then as you do backward elimination, it's z, y, x. What we did here was using equations in order to figure this out. You can actually make this a lot simpler on yourself by using matrices. Not only does it make it simpler in terms of computation because you're not having to deal with x, y's and z's being thrown in there as well, but it also means that you can plug this into a calculator, which is really, really helpful. So even in an exam, if I asked you to show the steps for Gauss-Jordan for me for a particular problem, you can always go ahead and double check your answer on a calculator, which is great. But 9 times out of 10, if they don't ask you to show your work, you can do this on a calculator, which is so helpful. So what I'm going to do here is, let's go back to our 3 by 3 example here. So I've got 3 equations in 3 unknowns. Okay, I'm going to write this in matrix form, and then you can see how we would have done this using matrices rather than having to deal with these x, y's and z's all thrown in as well. It's exactly the same method, it's just a lot easier in terms of visually when you are looking at this to go ahead and solve it this way. Okay, so if you go back and look at our 3 equations, we had 1x, okay, so the coefficient of x was 1, then the coefficient of y in my first equation was 2, and my coefficient of z in my first equation was 1, because I had x plus 2y plus z equaled 8. Then my second equation, I had 2x plus y plus 2z equaled 10. My third equation, I had 3x plus y minus z equaled 2. So what you'll see is on the left-hand side of this matrix, I have all of my coefficients where each row represents an equation. So I had 1x plus 2y plus 1z equaled 8. So my right-hand side after the line is all the constants that are on the right-hand side of my equals. Okay, so each row of this matrix is literally just representing one of my equations. I can then go ahead and use the 3 elementary row operations, but now I don't have to worry about my x, y's and z's being in the way. But I'm doing exactly the same operations, it just looks a lot easier. Okay, so we're going to go through this exactly as we did for our last example. I want to make sure, like I said, that my first variable in my first equation had a coefficient of 1. In terms of matrices, that means I want to make sure that this top left-hand element is a 1. Okay, that tells me that x in my first equation has a coefficient of 1. I then wanted to eliminate that x variable from everything below my first equation. What does that mean? That means that I want to make everything below that 1 a 0. So I want to make that 2 and that 3 a 0. How do I do that? Well, I take my first row as being the exact same because I'm not changing my first equation. Now this 2, I want that to become a 0. How do I do that? I'm going to subtract 2 times my first row from my second row. So my new second row is going to be my old second row minus 2 times my first row. So that's going to give me 0, and then 1 minus 2 times 2 is negative 3. 2 minus 2 times 1 is going to give me 0. 10 minus 2 times 8 is going to give me negative 6. If you go back and look, when we did that before with equations, we had negative 3y is equal to negative 6 after we had done that. Exactly the same as what this row represents. Then I want to make this 3 into a 0. How do I do that? I subtract 3 times my first equation from my third equation. So my new my third row now becomes my old third row minus 3 times my first row. That makes that a 0. Then 1 minus 3 times 2 will give me negative 5. Negative 1 minus 3 times 1 will give me negative 4. And 2 minus 3 times 8 will give me negative 22. Exactly the same in equation form. It's just now that we have this in matrix form. Okay. You go ahead and do the same thing again. I now want my second variable in my second equation to have a coefficient of 1. That means that this term here, I would like that to be a 1. I'm then going to eliminate or make 0 everything below that 1. So I would then eliminate this term here and make it a 0. Then once I've gone ahead and done all of that, I then make this entry here into a 1 by dividing my row through by a particular number, whatever it's going to end up being. Okay. So you're going to go ahead and do exactly to the rows what you did to each of our equations. And at the end of the day, you should end up with this matrix here. So what we've ended up with is 1 on the diagonal and 0s everywhere else on the left, and what is on the right are my solutions. So I've got x, 1 times x equals 1, y, 1 times y equals 2, and here 1 times z, which is z, is equal to 3. So you can then just read off what the solutions are. Like I said, this makes it so much easier because you're not having to deal with equations. You don't have the x, y's and z's in the way. You can just do these elementary row operations to the rows of the matrix rather than having all of these variables flying around and it getting more complicated, but it's exactly the same method. Okay, so I highly encourage you, whenever you get one of these problems, go ahead, put it into matrix form, where each row of the matrix consists of the coefficients of, in this case, x, y, and z. Your right-hand side is the constants. You make each one of your rows represent one of these equations, and then you go ahead and use those elementary row operations. When you do this, in order to double check what your solution is, I would highly recommend you actually plug these into a calculator. What I'm going to do is I'm going to show you, once you've converted this system of equations to matrix form like we have here, I'm going to show you how we can actually get to this form of the matrix just by using our calculator. I will tell you now that this specific matrix has a name, and it is called the reduced row echelon form of our initial matrix. It's called reduced row echelon form. When you get your system to be upper triangular, like we talked about before, so if we would have carried on with this particular matrix and made it into upper triangular form, that is called row echelon form. So you've basically reduced it some, but not the whole way. Reduced row echelon form is where you have made your left-hand matrix as simple as it can possibly get. So you've gone fully through both forward elimination, but also backward elimination. Reduced row echelon form is what you're actually going to see on your calculator. So I want you to be aware when you look at your calculator, this is actually what we're going to be looking at, because it's actually called on the calculator RREF. So I want you to know what that actually means. So I'm going to go back to my previous example where I had that 3x3 system with 3 variables and 3 equations. And I'm going to input that matrix into my calculator and put it into reduced row echelon form. And then we can just read off what our solution to the equations would be from this particular matrix that we get on our calculator. So what I'm going to do, you'll see right above this X inverse button, you see matrix. I'm going to go second X inverse. Okay. You actually, in order to input the matrices, you have to go across to edit. Okay, you can click on any one of these matrices that you like. I'm going to click on matrix A. You have, if you look at your particular matrix, you have a 3x4 matrix. It has 3 rows, 4 columns, if you include that last column that has constants. So you have to include that when you put this in. Kind of ignore the fact that the line is there when we wrote this matrix down. You have 3 rows and 4 columns. So you're going to click 3 by 4 and just type that in. Once you've done that, you then input your entries. So exactly as we wrote it down before. Remember that our first equation was x plus 2y plus z equals 8. So I've got 1, 2, 1, 8 as my first row. You then do the exact same thing for the remaining rows, for your second row and for your third row. Once you have done that and you've input the values, come out of this matrix entirely. So do second and quit. So you come out of the matrix menu and then go back in. Okay. That matrix A should now be stored as a 3x4 matrix in your calculator. Go across to math and you're going to go all the way down to option B. And you'll see it says RREF, reduced row echelon form. It's exactly what we want to look at, so we're going to click on that. And then you're going to go second and matrix again and click on matrix A. That is the matrix that we want to find the reduced row echelon form of. Click enter. And you'll see it's the exact same matrix that we got by hand. And we can go ahead and read this off as 1 times x, 0y, 0z equals 1. So x is equal to 1. Same deal here. I would have y is equal to 2, z is equal to 3. So I can just read my solution off from my calculator. So this is a much simpler way of doing it. It's also a great way to check if you do have to do Gauss-Jordan by hand. This is a great check to do at the end of a problem.